I would like to continue now and give the floor to our next panelist, Professor Ada Yonath. Ada, please, floor is yours.
So the coronavirus, the one we talk about now, is not just a new virus. It's another cunning parasite that uses the human system to translate its genetic code. And I want to talk about it a little. But first, you have seen all types of viruses. We are focusing on COVID-19 that you can see here. This will be more or less its size compared to HIV. But the real big one, the real long one, is Ebola, and I won't talk about it today. If one looks at really at the internal and external structure of COVID-19, so there is the spike protein that you just heard about, this green thing. You see also okay. There is a membrane, there are membrane proteins, and there is inside the genetic information as RNA, not as DNA, as RNA, and it is a sRNA, it means it's single strand, and it is going straight, positively. So if you look at the genetic organization of the virus, you heard that it has a polyprotein. This is the biggest thing. It comes with a protein that has a lot of places inside, pieces inside, and it cuts itself. So then it comes out with two very important proteins for its life, which are called PL and 3CL, but the names are not so important. What's important is that they are proteins. This means they can cut more and deliver more pieces that have to be translated. Then they have in the gene an RNA polymerase, the third one. This is a protein that polymerases the RNA. The RNA is the genetic information, so the virus has to make itself, to make its son and daughter and so on. So it has to polymerase, to make polymers of its RNA, and the spike protein that you just heard about, and so. And I won't talk about all of them. I'll just say that these two proteins that I showed in the beginning are really very important. They are very similar in many viruses. You can see here how they look. Although this looks a little bit more full, actually the active site is the same in the three of them. Neither of them is COVID-19, but you see how similar they are, and therefore there are some medicines, some drugs against it. They are essentially analogs for nucleosides, for RNA. You can see here some of them, and of course the one that is in the red frame, which is the one that has the possibility to be used. It was developed for another virus, but it works. And you heard earlier how it works. And it got the permission to be used. So if we talk about more specific examples, and I will not go into all, and just show three different ways of thinking. So there are antibodies from the plasma of recovered people, and this is done by a Japanese company called, can't see it here, but called Takeda, sorry. Merck is making vaccines which are really clever. They make a chimeric virus, they take a harmless virus and a piece from virus that they want to destroy or to kill or whatever, to eliminate, and they make from them a chimera. Maybe you can see it here on the left, a small one. So they combine the two of them. Now this can be inserted into the person in several ways, and it can develop vaccines without being poisonous. And then there is another one, which is alternative immunotherapeutics, which is actually done in the institute where I am by Dr. Ron Diskin. And he was already successful for Ebola. You can see here the Nature paper about it. So, as I said earlier, and I repeat now, all viruses are obligate intracellular parasites, and the replication requires host cell functions. And although the size and the composition of the functions of the virus are very diverse, remarkably diverse and complicated, it cannot do anything on its own. It needs the host. What does it mean? It means that it uses the way the protein biosynthesis way, the machinery of the cell. So in the cell, there is DNA, and it's being transcribed to messenger RNA, and then it is being translated to proteins by ribosomes. The virus comes only with RNA, so it starts here, but it doesn't matter, it is. And this step is monitored, controlled by microRNA, which I'll come back in a minute. So what we know about this machinery, we say that it is like a factory with 2 floors. At the top floor, the information is being read, and in the lower floor, the newly coming in amino acid is being connected to the growing protein, and the truck that brought it, if it's a factory, there is a truck, that it goes out together with other trucks. The messenger, the information will move by one codon for any amino acid. The protein will be longer, and the whole thing doesn't take a lot of energy. So actually, these 2 floors are the 2 subunits of the ribosome, and I want to show you a short clip, which was earlier. A short clip of how it's done. It doesn't start. So it's actually a complicated machinery. It has the ribosome is lived as 2 separated subunits in the cell, and they come together when they start. They have to start to. Oh, here it comes. It's time. Then they have to start. So the messenger RNA comes to the small subunit. You see the red thing here. And initiation factor is monitoring the entrance of the messenger into its place. And this is initiation factor. In bacteria, number 3. In human, there are many more initiation factors. Once this is okay, the first track, and it's another RNA molecule, transfer RNA, is being brought by another initiation factor, and it carries the first amino acid. And now can come the large subunit and associate itself with the small one. And the active ribosome has been made. So we can look at it now from the solution part. The top is the large subunit, the lower is the small. And you can see how amino acids are being brought in. Once at a time, it can make 40 bonds in a second. And they're going out, and the ribosome helps. So the decoding happens up. We took away the large subunit, so you can see the decoding. And the peptide bond between the amino acids is made here down, and the newly born protein goes into a tunnel. So now you can see the whole ribosome again. The tunnel goes through it, and the process continues until there is a stop codon that says, now stop, and another factor comes, this gold thing. It's a recycling one, release one. It will separate the 2 subunits. All the factors are going around, and the protein, the newly protein, is the blue one. So this is what the virus catches. when it comes to the something is missing to the cell. So it's really important to visualize what the virus can do in the cell, but also just a few days ago I found a new paper that talks about the difference in virulence for older people, that most of them just are much more sensitive and much more suffering from the virus than the young one. Here you can see on the right side in the table. So what I found written, for me it was new just a few days ago, is that this virulence in aged patients, it happens because microRNA, small RNA, that is playing a big role in controlling gene expression in normal people, it's very small. It's only 8 to 28 members. This one diminishes, the amount of it diminishes with age. And this one is also controlling not only gene expression, but also it is the front line for fighting viruses. So when it diminishes, there is less front line, and this may explain, at least partially, the fact that older people and diseased people have more mortality or suffering more. So just to show you where it plays here in the way between gene to protein. It sits here. It controls this. So I cannot finish this lecture, this presentation, without asking you a question that excites me. What happens when a virus comes into a cell? Can it recruit all the components of the biosynthetic machinery of the host, the initiation factors, the protein biosynthesis, the RNA? Can it do this? Can it make combine the ribosome from its two subunits? Or does it just jump into the queue using its RNA? What do you think really happens? So I have the question in another way, but it's not important, and I want to thank you.